Welcome to Chapter 7. So we have covered basic elements of circuits. We've covered resistors, we've covered capacitors, and we've covered inductors. Now we'll take a look at combining all of these elements into a single circuit. So let's take a look here. So we have analyzed these resistive circuits, so with resistors. So with our resistors. But then we also have these storage elements. The storage elements that store energy. They store energy. And the storage elements we have are the inductor, and also the capacitor. Okay, so we have the inductor, the capacitor, and the resistor. These are storage elements. The inductor stores energy. It stores it in a magnetic field. Okay? It stores it in a magnetic field, and the capacitor stores it in an electric field. So an electric field, a magnetic field here. So to approach these problems, to solve these problems, when we add these two in here, remember that, for example, a capacitor, the current through a capacitor is C dV dt, right? We have this relationship. And then through an inductor, we have the voltage is equal to L di dt. So what these have in common is time. They factor in time. They change with time. With resistors, right, we analyze problems at a steady state, But as we add inductors and capacitors into the circuit, we must take into account time. So in this chapter, we will be covering a new way, which we call a first order circuit. First order circuit. And this first order circuit is called this because it has a first order differential equation. So the first order circuit works with a first order differential equation that takes into account time. Time is the big thing here. So we will analyze these elements in circuits. We will analyze these with an addition to time. So let's go ahead and get started at covering some of these topics. We will first look at the source-free RC circuit. So let's take a look. The source-free RC circuit. So the source-free RC circuit. And what this means, source-free, this means free meaning no, source-free. So no current source, no voltage source. So current source or voltage source here, that is, we don't have this and we don't have this. So that is source-free RC circuit. The RC, this means resistor, this means capacitor. So let's draw this circuit here quick. We have a capacitor on this side, and it's attached to ground. And then on this side, we have our regular resistor. So this is our capacitor, and it has C, and this is our resistor R. And the voltage across here, we're going to call V. So this is the voltage, and the voltage across the capacitor is the same as the voltage across the resistor. So this is our source-free, no current source, no voltage source, RC circuit here. So let's take a look at this. And when we include time, we are going to say that at the voltage here, at time 0, this is the time, 0 seconds, is equal to V naught. That is just our original time, our initial voltage, here. So the voltage at time 0 is V naught. Okay. Now let's do our KCL here, and I'm going to grab, and we'll call this the current through the capacitor, and we have the current through the resistor. Okay, we have those. So since we have nothing, we're going to do in minus out here. We're going to do, or n equals out. We could do, let's do n equals out up here. So coming in, we have nothing. So we have 0. And going out, we have IR plus IC. Both of these going out. And we know that IR here is equal to the voltage divided by the resistance, R. And IC is a little trickier. Remember that the current through a resistor here is C dV dt. Okay, so that is the current through the resistor. We went through that in chapter 6. So that is equal to 0. And continuing on, so we have this equation, and we're just going to rearrange this equation. So we're going to rearrange it so that we have dV dt plus V over R C is equal to 0. So we just move this C down here. Okay, so we move the C, so now we have dV dt on this side. Now we're going to put this on this side over here. So we have dV dt equals negative V over RC. We're going to move the V over to this side and then move dt over to this side. So we have dV over V. We move that over here. And that is equal to dt over RC. So we have this equation set up, well, negative here. And we can write this as, maybe it's easier to see this if we write this as negative 1 over RC times dt. Okay, so where do we go from here? We take the integral of both sides. We integrate both sides. And the left-hand side here, if you remember, this is like 1 over x dx, integrating this. Do you remember this? That is equal, this side is equal to the natural log of v, or the natural log of x. That's what we have here. And if we integrate the left hand or the right hand side here, we get negative t divided by RC. Because R and C are constant. They are constant. They stay the same. So this is our integration. And then we need to make sure that we add on our constant. Remember, when we integrate indefinite integrals here, we have to add this plus c on. And what does this come out to be? What is c equal to? Well, what is c? Well, remember, when t equals 0, v is equal to v naught. Okay? So if t is equal to 0, that goes to 0. So we have natural log of v is equal to 0 plus c. So to make this work, c must be equal to the natural log of v naught, right? V is then going to equal the natural, or the v naught. Okay? So our equation, this equation, then becomes, let's write this out. Natural log of v equals negative t over RC plus the natural log of v naught. Okay, so we have this equation now. Now that we have this equation here, we're going to move this to the other side. So we'll move this to the other side. So we have natural log of v minus natural log of v naught is equal to negative t divided by RC. Okay. Now we can simplify this side. We can simplify this side over here. Do you remember from math where you have, if you have natural log of x minus natural log of y, this is equal to the natural log of x divided by y? So the subtract here then becomes division here. And we're going to do the same thing on this side over here. So that becomes the natural log of v divided by v naught equals negative t over RC. And this is the part where we take both sides and we take them to, we used e here. So we do both sides. And you remember that e to the natural log of z, right? That is just equal to z. We're going to do the same thing here. So by doing that, we get on this side, we get V over V naught is equal to E negative T divided by RC. And lastly, we'll move V naught to the other side. So the voltage at a specific time is equal to V naught, the original voltage, times E to the negative T divided by RC. Okay. So this is our first order differential equation for a RC, a source-free RC circuit. And we have a special name for this too. With no sources, this equation here is known as the natural response. Natural response, meaning that this is the way it behaves naturally with no voltage added or no current added. So this is what we call the natural response of the circuit. So with this equation here, this term RC, R times C, sometimes we call that the time constant. So, and we label it tau. Tau is equal to the time constant, which is then equal here to RC. So we can rewrite the equation as V of t is equal to V naught e to the negative t divided by tau. So that makes it more general. So we can use it for different values for R and different values for C. So as long as we have the R times C, we can find this time constant here. Now, if we talk about the time, it behaves in a certain way. So the time looks something like this. So we have our tau here, which is R times C there. And you see this curve as it goes here. So let's see if I can select this. All right. So we have tau here, and that is R times C. And if t is equal to tau, this here, V is equal to 0.368 V naught, the original voltage. So if t is equal to tau, we have 36.8% of V naught. Okay. So as time goes on, it gets closer and closer to zero. Closer and closer to zero here. So let's take a look. Let me grab this here. And in this table, we see that all the values for t in terms of tau. So 1 tau, if t is 1 tau, it's 36 here. 2 tau is right over here, 2 tau, and that is 13.5% or 0.135. 3 tau, 4 tau, 5 tau. This is almost zero. It's almost zero here after 5 time constants. 5 time constants here. Let's do a first example for source-free RC circuits. So I'm going to draw a quick circuit here. So we have a resistor, and a capacitor that are in parallel. And then we have 2 more resistors. And this resistor is 8 ohms, and this resistor is 12 ohms. And this capacitor is 0.1 farads, 0.1, and this is 5 ohms over here. Now let's label some voltages. We have here, we're going to call this Vx here, and this voltage here is Vc, the voltage across the capacitor, And then lastly, we have the current. We're going to call this Ix here, the current through this Vx. So what we want to find, we want to know, we actually know that Vc at time 0, at 0 seconds, is equal to 15 volts. And we want to find Vc, Vx, and Ix for t is greater than 0. So t for a time greater than 0. So we can use an RC circuit here. We have no sources. So let's first find the equivalent resistance of this whole circuit here. So if we find the equivalent resistance, we know that we have these two are in series. These are in series, which is then in parallel with this. So these are in parallel. So parallel. Okay. So Req, the equivalent resistance, is equal to 8 plus 12 in parallel with 5 ohms. 5 ohms, meaning parallel. So that is equal to 20. This is 20. 20 times 5 divided by 20 plus 5. So that is 100 divided by 25. Is that right? 20 times 5. And so the equivalent resistance here is equal to 4 ohms. Now we're going to redraw this circuit a little bit. We'll redraw this circuit. So what we have here is a capacitor, which is 0.1 farads. And then we have our equivalent resistance over here, which is 4 ohms. And the voltage across here, the voltage across this here from the top to the bottom is actually Vc. So this is Vc here. Okay. So by doing this, we can figure out our time constant, tau, is R equivalent times C, which is equal to 4 ohms times 0.1. And that comes out to 0.4 seconds. This is in seconds, 0.4 seconds. Our time constant is in seconds here. And plugging that into the equation, since we know that this is the voltage VC, VC is equal to V naught e to the negative t divided by RC, which is this tau, which is 0.4. And then we also know what our original voltage is. That is given in the problem here, 15 volts. So we can write VC is equal to 15 times e to the negative t divided by 0.4. So that is one of our solutions that we were looking for. So let's write that. That is the voltage across the capacitor. Now, let's erase some of this stuff. Let's go back and look at our original circuit. And what we have here is we know this VC now, and we're looking for Vx. So Vx, we can use voltage divider, which is going to be 12 divided by 8 plus 12 times VC, this voltage here. Okay, because up here is VC, and we can figure out the voltage across there using this. So that is then Vx is equal to 12 divided by 20 times 15 e to the negative t divided by 0.4. Right? So multiplying this out, that comes out to be, I believe that's 9. Vx is 9 times e to the negative t divided by 0.4. So now we have Vx as well. The last thing that we need to find is Ix. Ix. And this value here is going to be equal to Vx divided by 12. So remember, V equals IR. So if we know Vx, we can figure out Ix here. So Ix is equal to Vx divided by 12. So we have 9 divided by 12 here, which is going to be equal to 0.75 e to the negative t 0.4. And then this is going to be in amps too. So this is in amps, this is in volts, and this is in volts. Okay, so that is a quick example of how we took this circuit, this no sources, source-free, no sources, and combined all of the resistors first to find Req. And then by simplifying the circuit to this, we can then use our equation here to solve the rest of the circuit. We will now cover the source-free RL circuit. So this is source-free, meaning no current source. So no current source and no voltage source. Source-free. And this is a resistor and an inductor. So what we have here is a circuit that looks something like this. So we have an inductor And we also have a resistor. And we can call this R, and this is L. And here we have a ground. So what we're going to do is label the voltages through these. And we're going to have this be the voltage VR across the resistor. And this is going to be the voltage VL across the inductor, VL. And I drew this plus minus here because we're going to look at a loop here, a loop. And we know that the sum of the voltages around this loop, KVL, Kirchhoff's voltage law, the sum of the voltages around this loop must be equal to 0. So if we take a look, we have VL plus VR is equal to 0. Now we know the voltage, remember the voltage across the inductor is L di dt. The current, the derivative of the current with respect to time. And the voltage across the resistor here is just nothing more than this current I times R. Or we can write it as R times I is equal to 0. We're going to take this equation and let's move the Ri to the other side. So we get an equation L di dt is equal to negative R times I. And we're going to move this L to the other side as well. So if we move the L to the other side, erased a little bit. So that is negative R over L times I di dt. Now let's move the I to this side. So what we get is, and we'll move the t dt to the other side. So we have di over I is equal to negative R over L times dt. Now on the left-hand side we have current, and on the right-hand side we have time. So what we're going to do is integrate both sides. We're going to integrate both sides here. And the left-hand side, we're going to integrate from the initial current to the current at time t. So current as a function of time from the initial to the current. And then here we're going to integrate from 0 to t. 0 to t on this side. And if we do that, let's take a look. On the left-hand side here, we get the natural log of I, and we need to evaluate that from I naught, the original current, to this. And on the right-hand side, that is equal to negative RT divided by L, evaluated from 0 to t. Okay. This left-hand side becomes natural log of I minus the natural log of I naught. And the right-hand side becomes negative R times T over L minus R times 0 over L. So this term is 0. Now remember, we can simplify this term. This is the natural log of I divided by I naught here. And the right-hand side is just R times T divided by L. Now we can take the exponent here. We can take both of these to the E, or E to this, right? We take both sides, and that simplifies. We simplify those equations. This side just becomes I over I naught. And over here, we get e to the negative RT divided by L. And then we can just write I as I of t is then equal to I naught E times RT times L. So this I naught is the current at time 0, right? This is the initial current. So this is the equation here that we use for an RL circuit. And this looks very similar. It looks similar to a RC circuit, except we're dealing with currents here instead of voltages. We have a time constant. The time constant for this circuit, tau, is equal to L over R. Okay. So we can write this equation I of t is equal to I naught E negative t divided by tau. Okay. Because tau is L over R and this is R over L. So divided by tau here. And that is our time constant. So for this equation here, we can see that the response for the current here, once t happens, the current gets smaller and smaller and smaller. So we have this initial current and then it goes down here. And at t equals tau, the current at tau is equal to 0.368 of the original current here. So it looks very similar to the RC circuit in terms of its decay. This is what we call a decaying function, exponentially decaying. Exponentially decaying. So exponentially decaying here. Let's do a circuit problem example that is an RL circuit. I'm going to draw a circuit here. So we have an inductor which is attached to a resistor in parallel, which is then attached to a resistor and a dependent voltage source. And this resistor here is 4 ohms. This resistor here is 2 ohms. And this inductor is 0.5 Henry. 0.5 Henry. And we have several currents here. We want to know what I is, and we want to know what this current is, which is labeled IX. And this voltage source here is actually 3 times I. So it's 3 times the current here. All right, so to start on this problem, because we have an RL circuit, we would like to know the equivalent resistance. Well, that's a little difficult, and because it's hard with this inductor and these, But the equivalent resistance is going to equal the Thevenin resistance through the terminals here and here. We can call this A and B. So we're looking for the equivalent resistance here. So let's redraw the circuit by finding the Thevenin resistance. So we have here and we have this. And this is 3I. And we have 4 ohms here and 2 ohms here. Now, because we have a dependent voltage source, this is a dependent voltage source, we can't just say that these are in series or parallel and find the equivalent resistance. We need to use the property of linearity. Remember linearity? So what we will do is add a voltage source here. We will add a voltage source, and we'll say that this is 1 volt here. And we will look and see, the we'll look and see for the current coming out of here. So this current, which is I naught. And what we'll see here is we use this property of linearity where V equals I times R, where this is the Thevenin resistance. So if we know the voltage, 1 volt, I is going to be, well, R Thevenin will equal the 1 volt, this volt here, divided by the current I naught here. Okay. So that's how we'll use linearity here. So let's keep going. So we're going to do a mesh analysis. So let's draw the loops here. And this is going to be equal, just call this I naught. That will be the current here. And we'll call this I1. Well, this I is actually downward here. So what this is going to be negative 3 I naught, right? Because I naught is this direction, I is this direction. So we're just switching it. We're just switching that there. So let's do our KVL for our 2 loops. We have 2 loops here. We're going to do KVL. And we'll start down here. And we have negative 1, because we go negative positive, plus this 2, and that is I naught minus I1. And that is equal to 0. And let's simplify this. Let's expand that out. We have negative 1 plus 2 I naught minus 2 I1 equals 0. And then lastly, let's solve for I1. So if we move the 1 to the other side, and so we have negative 2 I1 is equal, well, I guess we could solve it this way. We have, we could do that. Okay, so we have negative 2 I1 is equal to 1 minus 2 I naught. And then we solve for I1 is equal to 1/2. That will equal I naught minus 1/2. So that can be our first equation. That is the first loop here. And let's do the second loop. the second loop, we will start here and go up where we have 2 times I1 minus I naught here. And then we plus 4 times I1 crossed here. And then we go positive to negative, which then is a positive negative 3 I naught equals 0. Now we can, let's expand this out. 2I1 minus 2I naught plus 4I1 minus 3I naught equals 0. So we have, that comes out to 6I1 minus 6I1 minus 5I naught equals 0. And then we can plug this into our I1. So we have 6 times I naught minus 1/2 minus 5I naught equals 0. Okay, so that's I naught minus 3 equals 0. So I naught is equal to 3 amps. So that is one part of the solution. We're not done yet. So if we know I naught is 3 amps, we need to go back up and we find that our Thevenin is then 1 volt divided by 3, which is 1/3 ohm. 1/3 ohm. Yeah, 1/3 ohm. So that is our Thevenin resistance, and that's the important part. This is the important part. So now that we've found the equivalent resistance, the Thevenin equivalent, which is going to be equal to 1/3 ohm, we can then use our equation. Remember our equation for the current as a function of time is equal to I at time 0 times e to the negative t over tau. And were we given in this problem, yeah, we were supposed to assume the current at time 0 equals 10. Right? That was this was given in the problem. I forgot to mention that, but that was given here. So we have I of t here. I of t is equal to 10 amps times e to the negative t over tau. And tau, remember, is equal, that is equal to L over R, which is equal to L over R equivalent. And we know L here is 0.5. And R equivalent is 1/3 here. 1/3. So tau, our time constant comes out to be 3/2 second. So 3/2 of a second. And then we can sub that in here. I of t is equal to 10 e to the negative 2/3 times t. To the negative 2/3 times t amps. So that is our current here. Now, what is our current Ix? Our current Ix. What is that? Well, what is the voltage here? The voltage here, right? We know the voltage through a resistor or an inductor, a voltage in an inductor a voltage in an inductor is equal to L di dt. So that's what we have for the voltage. So how do we figure that out? Well, we take, we know L, which is 0.5, and di dt, we take the derivative of this. We take the derivative, so di dt is equal, so this would come down, negative 2/3. So we have negative 2/3 times 10 times e to the negative 2/3 times t. Okay, so this is the current here. So we plug that in here. So what we get is the voltage across here is negative 10 divided by 2/3. 10 divided by 3. 10 divided by 3. So that's 0.5 times 2/3 times 10. E to the negative 2/3 times t. That's a 3. 2/3 t there. Volts. Okay, so that's the voltage. That's the voltage up here. But we still don't know the current here. But we know Ix is going to be equal to this voltage, V, divided by 2 ohms. 2 ohms here. So the voltage here divided by 2 will equal Ix. So we just take this Ix is equal to the voltage divided by 2, this divided by 2, which then we get negative 10/6 e to the negative 2/3 times t volts. All right, amps. There we go. Amps. There we go. So we have solved I for IT, for the I going through the inductor and the current going through the resistor here. And the way we did that is finding the equivalent resistance, or R Thevenin, for this circuit, and then we can use the equation for the time constant here. And getting that time constant, then we can use our general formula for current through an inductor right here. Okay. So sometimes we need to encounter circuits that are not continuous, that switch on and off. For example, we have a switch here. See if you can see that switch. So no current or no voltage. Now it has voltage, on and off. On and off. So we encounter this all the time in circuits. So we need a function that shows on and off. And what we call it here is called the unit function, unit step function. So if we call this the unit step function, unit step function here. And what this is, see if I can draw. So this is time t, and this is our unit step function as a function of time. This is time here. And what we see is when we turn something on, as we switch something on here, we see it goes from 0 to 1. 0 to 1. So it goes from 0 to 1. And this is what we call the unit step function. And we can write it in this manner. So we say u of t is equal 0. It's equal to 0 when t is less than 0. So over here, it is equal to 0. Over here, it is equal to 1 when t is greater than 0. So this is our unit step function. So, for example, if we have a voltage source, and we'll call this V naught, and right now it is disconnected. So it's connected in this manner. And we have A and B here. Right now, the voltage between A and B is 0, right? This is 0 volts here. Now, as we switch that voltage here, that becomes, we switch it and we connect it here. And now the voltage is V naught. So depending on how we are writing this, right, we can write this using this unit step function. So if we draw a voltage source here, we can simplify this by just writing A and B and writing this as V naught times the unit step function ut. And these two are equal. These two are equal. Because for this one, we have if t is less than 0, then the voltage AB is equal to V naught times 0, which is 0. If t is bigger than 0, the voltage AB is equal to V naught times 1, which is V naught. So this is a way to use a unit step function to simplify these two, because these two are equal to each other. We can also use the unit step function for current. So if we have a current source, I naught, and we have terminals A and B, and we're looking at the current here. And if we want, we can put a resistor in between here. It doesn't matter. All right, so if we have this function here, when t is less than 0, then I is equal to I naught times 0, which is 0. So this is equal to 0. But if t is greater than 0, I is equal to I naught times 1, which is just I naught. So we can use this function like we're switching things on and off. So this is the unit stepwise function. Now what about the derivative of this function? So we have this function here, and it is 0 for t less than And then it is 1 for t greater than 0. So this is 0 down here. This is 1. And in between here, it's just a vertical line. So we have this. So we can use also the derivative of the unit stepwise function. And if we take the derivative, we're going to get the derivative here is 0 when t is less than 0. The slope of this line, the slope, it's exactly horizontal. So the slope is 0. So the derivative is 0. And it is also 0 for t is greater than 0. So the slope here is exactly horizontal. So it is 0 for t is equal to 0. Now, for t is equal to 0 here, it is undefined. Undefined, meaning we don't know. We don't know because it shoots straight up in the air here. Okay, it's undefined. And this term is called here the unit impulse function. And it is also known as the delta function. Because we write this is equal to delta times t, or delta of t. This is the Greek letter delta. The Greek letter delta. So we sometimes call this the delta function here. So up until this point, we've looked at source-free RC circuits and RL circuits. So what happens when we add a source? When we add a source, sometimes we say add an excitation source. So if we do that, we could think of it as having a source here and a resistor, and then we have let's say a switch and a capacitor here. So this capacitor, and we're looking for the voltage across that capacitor. And this is our voltage source here. And at time 0, time equals 0, t equals 0, this becomes a closed circuit. So then it becomes a closed circuit. So what we need to find to be able to solve these problems is the initial, let me make sure I spell initial right, initial capacitor voltage. So the initial capacitor voltage, which we would say is V naught, or we could say that is V of 0. This initial capacitor voltage. And 2, what else we need to find is the final capacitor voltage, which is going to be labeled our V infinity. Infinity meaning way into the future. Way into the future. And lastly, 3, our time constant. Our time constant. So we need to know all three of those things: the initial capacitor voltage, the final capacitor voltage, and the time constant. So if we do that, if we do this, what we can do is, in this situation, we take a look at t less than 0. T less than 0. This is an open circuit here. And in this case, we would find that the voltage across this capacitor at t is less than 0, and the voltage at time 0 is equal to 0. Right? Because no current is flowing. This source is not connected here. Okay. Our V at we would then take a look at t is greater than 0, and we would find t infinite, because we would have this source here, Vs, and then the circuit with our capacitor and our resistance. And at t infinity, no current is going to be flowing, and the voltage across here is going to be equal to this source voltage. So we have Vs would be our time infinity. And last, we need to find our time constant, which is then R times C, sometimes R Thevenin times C, with respect to these two terminals. And once we have R times C here, then our equation for the voltage at a certain time is V infinity plus our V at time 0 minus V infinity times e to the negative t times tau. And then all we would need to do is plug in our values here. And then this here is RC. And then that would be our voltage for time is greater than 0. Okay, so let's look at a RL circuit with a source. So if we have a voltage source here, and then we have our system that has a switch in it, and the inductor over here, and this is R, this is L, and we're looking for the current through the inductor, and this here closes at time equals 0, and this is our voltage source Vs. Okay, so if we do this, we need to find three things. We need to find the inductor current at t equals to 0. So this would be I of 0. That would be the current here at time 0. The second thing we need to find is inductor current at time infinity. So at very far in the future. And then lastly, what we need to find is our time constant. So time constant. So how do we solve this problem? Well, we first look at t is less than 0. Okay. T is less than 0. This is an open circuit. There is no current flowing through here. There's no current. So I at 0 is equal to 0. Now we need to move to t is greater than 0. And when t is greater than 0, we have a circuit that looks like this. And this is L, and we're looking for the current I through here, and this is R. Now, if we look at this circuit, we need to find the inductor current at I equals infinity. Well, at I equals infinity, this here is acting like a short circuit. After an extended period of time, that acts like a short circuit. So at I at infinity is equal to the voltage source divided by R. Okay. That is equal to the voltage source divided by R. And then so this was step 1, step 2, and step 3 is to find the time constant. And the time constant is found, we need to find R Thevenin. And to find R Thevenin, we first open up these terminals. So this is our A and B terminals. We're looking for the resistance, the equivalent resistance here, and we have an independent voltage source, which we then turn off. We turn off that here. So our Thevenin resistance is just R, and so our time constant is R times L, or L over R, I'm sorry, L over R, which we then have L over the Thevenin resistance. Okay, so we have all three of these things, and we use the equation, the current at time t is equal to t, or I infinity, plus our I of 0 minus I infinity, e to the negative t divided by tau. So if we plug everything in that we did up here, we have our I infinity, which is Vs over R, plus I of 0, which we said was 0, 0 minus this, which is Vs over R, e to the negative t times R Thevenin divided by L. So this is our current as a function of t here. So these are both ways, both with a capacitor and an inductor with a source.